The HL addendum for applications of integration, Chapter 19, Section A, number 3. Find the exact value of the area of the region bounded by x equals y squared plus 1, the y-axis, and the lines y equals 1 and y equals 2. Let's see. Let's try to draw this out. So if we got the x and the y-axis here, so our boundaries are going to be the y-axis, the lines y equals 1 and y equals 2. Let's say it's here and here. And the function x equals y squared plus 1. Okay. Now to do this problem, it's not necessary to know what x equals y squared plus 1 it looks like, but if you do want to know what it looks like, it's a little easier to see what it looks like if you make it all equal to y equals. So what we're going to do is we're going to rearrange it. The x minus 1 with algebra, right? And we're going to divide both sides by square root. So it'll be square root of x minus 1 equals y. So this is the function. Basically, the square root of x minus 1 equals y looks like this, kind of like this, okay? So if I make the boundaries with the y-axis, y equals 1, y equals 2, and this function here, it looks kind of like that, right? So the area I'm going to look at is like that, okay? But you don't have to see what the graph looks like to do this problem, because they gave you everything pretty much the way you need it. So if I want to make the limits of integration y equals 1 to 2, I put them there. I put the function itself in x in terms of y here. And then I put dy. So then to take the derivative, I just take the integral. I take the integral of each one of these elements separately. And I end up with that, right? So I end up with 2 cubed over 3 plus 2 minus 1 cubed over 3 plus 1. And let's see, 2 cubed over 3 is 8/3. 2 is 6/3, so it'd be 14/3 minus, and 1/3 plus 1 is 4/3, so it's minus 4/3, so it's equal to 10/3. So the only difference between this problem and the core problems, or the SL problems, is the SL problems pretty much always have you doing things in terms of dx and not dy. The only thing you do on this is you invert everything. So like instead of having x equals 1 to x equals 2, it's y equals 1 to y equals 2. Instead of dy, it's dx. And instead of this expression here being in terms of x, it's in terms of y. So that's it. Here's the HL addendum for applications of integration, Chapter 22 in the HL book. Section A, number 3. Find the exact value of the area of the region bounded by this curve, the y-axis, the lines y equals 1 and y equals 2. Now the reason why this is HL material, not SL material, is because in the SL, what you're going to get is everything with x and y inverted. So the borders of the region that you're going to find the area of would be written all in terms of x, right? And the area and the integral would be done with respect to the x-axis to the y-axis. So you would say, oh, okay, so like x equals 1 corresponds to this line here, y equals 1, or x equals 2 corresponds to this line here. The x-axis is this border here, and then y equals x squared plus 1 is a curve like that, and I'm finding this region, right? And when you do this problem for HL, everything is in relation to the y-axis instead. So instead, we're going to be doing this function, which is an x function in terms of y. We're going to use the y-axis to the x-axis, and y equals 1 and y equals 2 for the limits of integration instead of x equals 1 and x equals 2. Just to review, for SL, this integral here in terms of the x coordinates would be x equals 1 to 2 here. The function would be y equals x squared plus 1. and it would be the integral in terms of dx. Okay, so it's going to be all inverted for this problem here. So let's erase all this, and then we'll do the real problem. Okay, so first of all, to graph this, we're not used to graphing a function x in terms of y, so sometimes it helps to solve in terms of y. So we would subtract 1 from both sides, we get x plus 1, and then we take the square root of both sides, and we would get y equals the square root of x plus 1. If you remember, y equals square root of x plus 1 is the square root function moved 1 to the right, so it looks kind of like this. The lines y equals 1 and y equals 2 are horizontal lines at these points here. And the y-axis is here. So basically we have a region which is like a sideways region of what we just saw in the other picture. Okay? And so if we were to write the integral that would solve this problem, it would be the integral from y equals 1 to y equals 2 of y squared plus 1 dy. And then we just need to take the integral of each one of the elements inside. So that would the integral of y squared is y cubed divided by 3 using the power rule. The integral of 1 is y. And we're doing everything in terms of dy, so that's why everything we treat the variable in question as y and not x. The limits of integration are 2 and 1. So then we plug in 2 for y cubed, that gives us 8/3. 2 for y, which gives us 2. And then we subtract off the values by plugging in 1, so it would be 1/3 plus 1. So if we're going to simplify this, it would be 8/3 plus 2 would be 8/3 plus 6/3, it would be 14/3. And then 1/3 plus 1 is 4/3, so it would be minus 4/3, so my answer is 10/3. Okay, next problem. On the same set of axes, draw the graphs of the relations y equals 2x and y squared equals 4x. Let's see, y equals 2x is a straight line. Remember, y equals mx, so the slope is 2, so it looks kind of like that. Y squared equals 4x. Let's see, in terms of like written with y on the left isolated, we would say y equals square root of 4x, okay? And it says to draw the graphs of the relations because actually, if we want to be pretty accurate about it, we would need to put plus or minus square root of 4x when we do find the function in with y on the left. And so basically that gives us a sideways parabola, right? Kind of like that. And we're only going to need half of it, but let's see which half we're going to need. Determine exactly the area of the region enclosed by these relations. Okay, so now you can see that like we're only talking about this region here. We don't need to have the bottom half of this. So really in the end we want y equals positive square root of 4x. We don't need to have the negative square root of 4x. Okay? But when we write our integral, we are not going to write it like this because actually what we want to have is an x value in terms of y, okay? And so in that case, this function here is going to be x equals y divided by 2. We want x on the left by itself. And this function here is going to be x equals y squared divided by 4. Okay? Now I am going to take a look at my drawing, and I'm going to label my drawing. This one here, this line here is x equals y over 2. And this line over here is x equals y squared divided by 4. Okay? And so I can see if I was going to take the integral of this, the limits of integration would be from here to here, right? Let's see, where do these two intersect? Well, they definitely intersect at 0, y equals 0. This point over here, we're going to have to solve the equation simultaneously to see when they intersect. So y equals 2x, I'm going to plug in y equals 2x. Instead of x, I'm going to put y squared divided by 4. And then I can divide both sides by y. I'll get y equals 2. Is that right? Yes. So y equals 2 is the intersection point. What is the x value that corresponds to y equals 2? It would be x equals 1, because if I put y equals 2 there, I'll see that 2 equals 2x, so x equals 1. So the intersection point is x equals 1 and y equals 2. So my limits of integration would be 0 and 2. And then in here, I'm going to put, I'm going to draw this with 2 different colors so you can see. Like the line, let's say, is the green, and the sideways parabola is purple. So what we're going to do is we're going to do green minus purple, because the green is the bigger number and the purple is the smaller number within this range of y equals 0 and y equals 2, right? So I'm going to put the equation for green here, which is y divided by 2, and then I'm going to subtract the purple equation, which would be y squared divided by 4. Okay, and then I'm going to put dx or dy because we're integrating with respect to y. Now we can do the rest. Okay, so now I'm going to integrate each one of the elements inside. And now, we've already done the hard part here. So the integral of y divided by 2 is y squared divided by 4. The integral of y squared divided by 4 is y cubed divided by 12, and this is with respect to y, right? So now I'm going to take the integral of each term separately, and so that would be, or I already took the integral, or did I take the integral? Yeah, I already took the integral. So actually, I did this wrong. This should be, I've already taken the integral. So once I take the integral, the limits of integration go off to the right side here, right? 2 and 0. Now I'm going to plug in the 2 and the 0, so the 2 goes in first. So it would be 2 squared over 4, which is 1, minus 2 cubed over 12, which is 8 twelfths, also known as 2/3. And then if I put 0 in here, 0 over 4 is 0. 0 over 12 is also 0. 0 minus 0, so this is 0. And so I end up with 1 minus 2/3, which is 1/3. And I think that's it. Okay, let's look at this one. A region with x is greater than or equals 0 has boundaries defined by y equals sine x, y equals cosine x, and the y-axis. Find the area of the region. Okay, so let's draw this first. So, y equals sine x, remember, starts at 0, 0. Y equals cosine x, remember, starts at 0, 1. And the y-axis. So let's outline those three. So we got the y-axis, y equals sine x, and y equals cosine x. Find the area of the region. There's two ways to do this problem, and I think the easiest way is with respect to x, because we already have the functions in terms of x, and also if you look at this function, if you cut it up into slices this way, you're only going to have one inside part of the integral. You're going to have the top function minus the bottom function. And if you try to do it sideways like this, then you're going to have to divide into two sections, which is just going to make more work for you. So this one is going to be in terms of x for a couple reasons that I gave. Okay, so let's see. We're going to have the integral, and what are the limits of the integral? The limits of the integral are going to be from 0 to the intersection point of cosine and sine. The intersection points of cosine and sine are pi over 4, because at pi over 4, sine and cosine both have a value of square root 2 over 2, right? So I'm going to have the limits of the integration be x equals 0 to x equals pi over 4. Okay? Pi over 4. And then the inside of the integral is going to be the top function, which is cosine of x, minus the bottom function, which is sine over x. So it'll be cosine of x minus sine over x. dx. And that's it. So let's find the area. The way we find the area is we're going to take the integral of each one of the elements inside. The integral of cosine x is sine x. The integral of negative sine x is plus cosine x. And so we've already taken the integral, so we're going to write pi over 4 and 0 as the limits of integration. And then we're going to substitute pi over 4 into each one. So sine of pi over 4, remember I just said the square root of 2 over 2. Cosine of pi over 4 is also square root of 2 over 2, both positive. And then we're going to subtract the cosine and sine at 0. The sine at 0 is just 0. The cosine of 0 is 1. So basically we got square root of 2 plus square root of 2 is square root of 2. And then minus 1. And so that is our answer. We don't need to change it to the decimal because this is an exact answer, and mathematicians like exact answers. Okay, find the area enclosed by y equals x cubed minus 5x and y equals 2x squared minus 6. Okay, so this is a tricky one, isn't it? First, you kind of have to like graph them because they didn't give you the limits of integration, right? So instead of, making an XY table or something, I'm going to factor each one, because remember factor the first one, because the factoring tells us something about where the x-intercepts are. So that's going to help us. Oops. Okay. So that's the factorization of x cubed minus 5x. So I know that it intersects the x-axis at 3 points. At 0, at positive square root of 5, and negative square root of 5. Square root of 5 is about 2 something, okay? So there's one intersection there, and there's one intersection there. And x cubed minus 5x, that's like a regular, gets bigger on the right side, gets smaller on the left side. So basically, it should look kind of like this, okay? So even without the calculator, you can kind of predict what the graph of this complicated looking function looks like just by factoring. Now what about the parabola? This one's pretty easy, right? You have a parabola that is lowered by 6, and basically it's not shifted to the left or right at all. So you're going to have something that starts 6 units below, and then it goes up, kind of like that. Where is it going to intersect the x-axis? Well, we can figure out where it intersects the x-axis by doing a factorization also. So it would be equal to 2x minus square root of 3 and x plus square root of 3. So its x-intercepts are going to be at negative square root of 3 and positive square root of 3. Square root of 3 is about 1.7, so negative 1.7 and positive 1.7. Okay, and I am just going to shrink this down because I just occupied the space of my next problem. So I'm going to put it right there. Find the area enclosed by these two. And so basically, I guess what that means, it would be this region here, right inside. Okay, so what's the easiest way to do that? The easiest way to do that, and again, since we get our equations in terms of x, it's better to just use a traditional integral, slicing it in this direction. So it would be integrating from the intersection points, which we haven't figured out yet, and inside we're going to have the top function, which is the red function, minus the orange function, which is the bottom function. So that would be minus 2x squared minus 6. And then it would be in terms of x, because we sliced it in the y direction. And then we just need to figure out the limits of integration. The way we could figure out the limits of integration is if we solve simultaneously these two equations and find the intersection. So that would be, let's see, we could say x cubed minus 5x equals 2x squared minus 6, x cubed minus 2x squared minus 5x plus 6 when does that equal to 0? So if we found the roots to this equation by, non-calculator means or by calculator means, that would find the intersections. But I don't want to spend a lot of time on that procedure right now because, first of all, we haven't done the chapter yet where we do that using synthetic division or whatever. We haven't reviewed it since 10th grade. And this isn't the main part of this. Finding the intersections is not you would usually probably do it with technology on the exam also. So let's find the intersections by using technology. So the way we're going to do that is we're going to enter both functions into the calculator. And then I'm going to graph it. And you can see that it's actually much more complicated than I had imagined. I had this parabola, I had this cubic, but look at it. It actually crosses in 3 different places, not in 2. So let me zoom in a little bit by changing the window size. I'm going to change the window size to -5 and 5 instead of 10 and 5. A -10 and 10. I'm going to do -5 and 5. And when I do that, we'll probably be able to see the intersections a little bit better. Okay, and here's the tricky thing on this one. If I want to find the area enclosed by the curves, do you see how this part of the curve and this part of the curve are actually 2 separate areas? And, if I did something like, oh, I'm going to do purple minus orange, for the left section here, the big section, it would be purple minus orange. But do you see how this part here, the orange is actually on top of the purple? So this part here would be purple minus orange. This part here would be orange minus purple. So I can't do the same subtraction for both. So actually I need to separate this into 2 different domains. One of the domains is going to be from here to here, and the other domain is going to be from here to here. Either way, we're going to have to figure out every single one of these intersections. This intersection, this intersection, and this intersection. In order to do that with technology, the easiest way and the most intuitive way, in my opinion, is to graph it and then do second calc intersect. And so if we do second calc intersect, first curve is the x cubed curve, yes. Second curve is the x squared curve, yes. Why is it asking me that? Even though there's only 2 curves, the calculator is kind of dumb. It does all cases where there's multiple curves, so it's always going to ask you which curves, even if it's obvious and there's only 2 curves, okay? What's your guess? The reason why it asks for a guess is it always starts out here in the middle. I want 3 different intersections. In order to tell it which intersection I want, I need to position the cursor closer to the intersection that I want. So for example, I've got the left intersection. By positioning the cursor close to it, it tells me that the intersection is -2, 2. I'm going to write that down here. So my first intersection is -2, 2. My next intersection is going to be this one here. Let's try to find that. Second calc intersect, which is number 5. First curve, second curve, yes, yes. What's your guess? I'm going to move my cursor close to this other point, hit enter, and it tells me that it is 1, -4. 1, -4. And now I need my last intersection, which looks like it's right at the edge of the screen here. Hopefully it's not off the screen. If it's off the screen, I might have trouble finding it. So let's try, see if it is on the screen. Second calc, intersect, and then first curve, yes, second curve, yes, and then we're going to move the cursor close to that point and see if it picks it up. It did, 3, 12. So there's 3 intersections, and actually we're more concerned with the x-coordinate of these intersections instead of the y-coordinate, and the reason why is because since we're doing this integration in terms of x, we only need the x values to find the limits of integration. And remember, not only do we need the x coordinates for the limit of integration, we need to figure out that we need to divide this picture here into 2 sections, right? This section and this section. So we're going to do 2 integrations. One of the integrations is going to be for this section, and the other is going to be for this section, okay? So I'm going to just do, first I'm going to do I'm going to have the red minus the orange here. I'm going to put it right there, okay? And then I'm going to have the dx here. But I want the absolute value of the difference, and I'm going to integrate it from -2 to 3, which are the outermost limits. But then I'm going to break it up into two different sections. And the first section is going to be the red minus orange, but the limits are going to be from -2 to 1. And then in the next section, I'm going to integrate from 1 to 3. And in this next section, instead of red minus orange, it's going to be orange minus red. So I would have like the regular difference function here, and then here I would have the negative of the difference function, because I'm going to do orange minus red, right? So let's do the first one. We'll do the integral from the first one. And then we just take the negative of that for the second integral. So remember that the expression, it happens to look exactly like this expression here. So it's going to be x cubed minus 2x squared minus 5x plus 6 minus 5x plus 6 dx. And then I'm going to take the integral of that. Okay? So I'm going to take the integral of this. It's going to be x to the 4th over 4 minus x cubed divided by 3 times -2 on top. Then minus 5x squared divided by 2 plus 6x. And then I'm going to take the integral, or I'm going to take the definite integral from -2 to 1. I'm going to add that to the second integral. And the difference between the first and the second integral is everything's negative. So it's going to be the inside of the second integral is going to be from 1 to 3 again, but it's going to be negative x cubed plus 2x squared plus 5x minus 6dx instead, right? So the integral is also going to come out everything inverse. So instead of x to the 4th over 4, it would be minus x 4th over 4. And then instead of negative 2x cubed, it's going to be positive 2x cubed over 3. Instead of minus 5x squared over 2, it's going to be plus 5x squared over 2. And instead of plus 6x, it's going to be minus 6x. And this integral is going to be from 1 to 3. So we're going to do two separate integrals here. And let's see. So this will be 1/4 minus 2/3 minus, I'm just putting in 1 for everything, right? Minus 5/2 plus 6. And then I'm going to subtract. I'm going to put -2 into everything now. So -2 to the 4th is 16. 16/4 is 4. -2 cubed is -8 times -2 is 16 plus 16/3. -2 squared is 4. 4 times 5 is 20. 20 divided by 2 is 10, so minus 10. And -2 times 6 is -12. Okay, now let's do this last section here. So we're going to have 3 to the 4th is 81, so -81 to the 4th, plus 3 cubed is 27. 2 times 27 is 54. 54 divided by 3 is something like 54 divided by 3 is 3 times 6, 18. 18. Let me just check that. 3 cubed, 27, 54, 54. Yeah, okay. And then 3 squared is 9. 45 divided by 2 minus 18. And then finally I'm going to have minus, and then I'm going to put 1 in for each one of these expressions here. So it would be -1/4 plus 2/3 plus 5/2 minus 6. Okay. So you got a bunch of fractions here to try and add together, and this is going to be a real pain. We could just try to do some of these with the calculator. So I'm just going to do each one of these with the calculator, and I'm going to write the result below, and you can join back in 2 seconds. Okay, so I added up all these fractions, and the calculator gave me 21.0833334, and I converted to a fraction by doing math, and the first function that comes up when you press math, and it gives me 253/12. Okay, so I'm just going to put the answer down there, and I can add up and fractions pretty easy on the calculator just by writing them out like this without parentheses. Okay, because of PEMDAS, the divisions and the multiplication of the fractions happen before they add and subtract, so it's pretty easy to do those without inputting a lot of parentheses. So that is the answer for that one. Last one, 15C. Y equals 2x cubed blah blah blah, and y equals x cubed blah blah blah. Okay, so this is similar to the last one, where we need to be careful maybe of how many intersections there are, and to see how many intersections there are, we could do it without the calculator by finding where these two are equal to each other. So we could do 2x cubed minus 3x squared plus 18 minus x cubed minus 10x minus 6, and that would give us x cubed minus 3x squared plus minus 10x plus 24 equals 0. When does that happen? Okay, that's not trivial. Okay, and again, let's just use the calculator. So I'm going to put in this function in y1 and this function in y2 and join back in 1 second. Okay, I have my two functions here in y1 and y2. When I graph them, they don't exactly fit on the screen, so I'm going to do a zoom fit, which is option 0. See if that improves the graph. Okay, there's one of them. And here's the other one. And that didn't really improve it that much. I think I am going to try to reduce this maybe to like negative 20. So negative, this will be the y I'm going to adjust. Oh, look at that. 22,000. That's just what I needed. No, I don't think so. So zoom fit is not always the best option. Okay, now let's graph it. See if that helps. Okay, there's one. Maybe go a little bit higher than that. And there's the other. And let's adjust the window size, maybe like negative 50 to 50. Negative 50 to 50. Oops, not that one. This one. The y's is what I want to change. Negative 50 to 50. See if we can see all the intersections now. Ooh, that's not what we wanted. Let's go back again. Negative 50 to 50, not 5. Okay. Okay, there's one of them. And there's the other one. So we want to find the area between the two. I can see that it would go from here to here. So let's find the intersections. Second calc, intersect, number 5. First curve, yes. There's only 2 curves, so. And let's find the left intersection first. Enter. The left intersection is negative 3, comma, negative 63. Negative 3, comma, negative 63. That's one of the intersections. The other one's up here. At least we're not going to have to like do what we did before. Second calc, intersect, first curve, yes, second curve, yes. And then we'll move the cursor to the right intersection, enter, and the other intersection is 2, comma, 22. Again, so let's try to find the one last intersection, maybe higher up here. So the way I'm going to do that is I'm going to repeat second calc, intersect, and hopefully first curve yes, second curve yes. And now I'm going to move the cursor up to here. And let's see, I think there's one more intersection here. And it didn't find it because it's off the screen. So let's do another window, and then we're going to change the y max value to maybe 100 so we can see the other one. And then we'll change the y min value to 0 because we don't need that part anymore. Now let's graph again. Oh, and so do you see how like there's an intersection here that you can't really see very well? Let's see if there's an intersection right there. So we'll do second calc intersect number 5. First curve, yes. Second curve, yes. And then we'll move the cursor close to there, and then we'll hit enter. And it says 4,98, so there is another one there. Okay, so we have 3 intersections. So it's kind of like the last one where we, like, you know, okay, so we have the red curve. We have the red curve. And we have the orange curve. And like, sometimes the red curve is above and sometimes the orange curve is above. So when we do the subtraction, we actually kind of need to either separate it into 2 sections, right? Into the section -3 to 2 and the section 2 to 4, or we need to take the absolute value, okay? And if you're going to use technology, you can do it all in one step, and since this is a pretty hairy problem, we'll do it with technology. So we're just going to put the outside 2 limits, -3 and 4. We're going to ignore the 2, but we're going to put the expression inside absolute value. And just to make things easier, we could put the expression inside the absolute value simplified as the left side of this, right? Because if we subtract the red minus orange, we're going to get x cubed minus 3x squared minus 10x plus 24, right? So let's do that. And we're going to do it all with technology now. We're going to say, and here we're going to do this with the integral function. So we'll do math, and then we're going to do integral fn int, and then we're going to say, okay, I'm going to graph, or I'm going to take the integral from -3 to 4, and then in the inside here I'm going to put absolute value, which, let's see if this is math somewhere. I don't see it. Is it number maybe? There it is, absolute value. And then I'm going to put in x cubed minus 3x squared minus 10x plus 24 dx. And let's see what it gives me. Is it thinking? Wow. 100.749999. Is there? Let's see if we can change that to a fraction. No, we can't. Okay, so the answer is 101.75 basically. 101.75. Could we have done this the same way we did the last one, where we separate it into 2 sections, do an integral from -3 to 2, and then do another integral from 2 to 4, and we do red minus the orange for the first section and orange minus red for the second section? Yes, we could. And then we could have done the integral analytically and not use the calculator for anything if we wanted to, but it would have taken a really long time, and you know, on the exam, they won't be asking you such a long integral problem because they don't want to waste all their time figuring out if you can do an integral by hand when they could have given you a simpler problem doing an integral by hand and known whether you could do it or not. So if this was on paper 2, for example, they would want you to take advantage of technology and to do all the shortcuts you can. So finding the intercepts using the calculator, the limits of integration, putting an absolute value instead of separating the sections, etc., etc. Those are all tricks that they would want you to use with technology on the exam.